So we're going to take a look at problem set number 3. Number 4, somebody's going to share their screen so we can see what they got. We can talk about it. Oh, is somebody trying to share and I haven't allowed sharing? That's probably why. Way to go, Steve. Okay. Okay, try it again.
I know mine's wrong. I don't want to share.
Well, that's okay. If you know yours is wrong, that's okay. It makes it a lot easier for us to kind of talk about. But does anybody feel confident about theirs? Let's start with that. Does anybody feel confident about their answer?
All right, so I'm just gonna say I don't know how confident I feel about it, but Steven and I kind of worked on it a little bit, not together, but just like talked about it. So
You guys worked so hard on it that you broke his computer.
Is that what happened?
It probably. Let's see what you got.
Okay, so for number 4, it's a little bit ugly, but it's okay.
Oh, I like it. But you did a nice job with that, with the drawing. That's cool. Okay, so yeah. What would the axes be for the graph that you have drawn here?
Oh yeah, I forgot to label them, but this should be T, the horizontal, and then this should be Y.
Yeah, so notice the axes for this graph for both number 4 and number 5 are going to be Y versus T, because we want to produce basically the slope field, right? And the slope field is always dependent variable versus independent variable. But the graph that I gave you is f of y versus one of the variables, either t or y, right? So the axes are completely different. The number one problem that I run into with this, or the number one issue that students have with these problems, is they want to try to draw the slope field on top of the graph that I gave you, which is not fair, because they're completely different axes. So nice work. So explain to me how you're thinking about the problem led you to draw it this way.
Okay, so mostly what I looked at was where it crossed the axis on the problem set graph, where it crossed the axis, and I just said that was where it was at 0, so that should be the equilibrium solutions.
Yep.
And I made the horizontal lines there to show that it's 0.
Exactly.
0 slope.
Slope would be 0. And so notice what we have. The solution is a slope field that looks like the same graph shifted vertically, right? And we did that together. We saw those last time, and you saw those in the notes, that the slope fields that look the same vertically are the ones that depend only on the independent variable, right? Because no matter where you look horizontally, they'll have the same slope vertically. So nice work.
Thank you.
Yay. Anybody want to show us their answer for number 5? Show us what that looks like. Now that Emma can feel confident in her answer, although she didn't label the axes, everything looked great. It's okay. You think that I would like dock you points for that? Oh yeah. Oh yeah, I will. Anybody else? Breach. What about you, Breach? Come on. He's like, no.
I completely thought about the problem 100% incorrectly.
Okay, but can you imagine what it would look like? So for example, let me share a screen with you. I'm going to share a screen, and I'm going to have you guys use what's called, you're probably familiar with it. If you've been in Zoom much, you probably know something about it. Do you know how to use the annotation features of Zoom? You like it? Like, welcome rate fans, get it? Because we're in a differential equations, because it's calculus, get it? Right, fans? Oh, man, you're a tough crowd. You really are. Okay, so what I'd like for you to do is, yeah, somebody knows how to do it. So if you move your cursor to the top of the screen, and one of the options should be annotate. If you click on that, you'll get a palette of things that you can do. And you can actually add stuff to this screen. Hey, there you go. Somebody drew that octopus that I was referring to earlier. or maybe that was a sponge or a cloud or something. You are doing this right, although in a font color that makes it really difficult to see. Lovely. So you can stamp things, you can add text to things, you can draw on things, and then of course you can also erase things. So if you go in, I'm, for example, erasing those hearts, just click, 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 erasing the hearts, right? Kind of nice. Here's what I want you to do. I want you, and I'm gonna move this up so we get a nice clear screen. I want you to borrow, yeah, I'll erase this stuff here. I want you to take a chunk of this screen and as small as possible, kind of off to the side or somewhere in the middle. I want you to draw me the axes for the slope field for number 5 and label the axes. You don't have to draw anything else other than the axes. Somebody's brave. Holy cow, that is a giant T. Is that supposed to be an S? I don't know what that is. Here, let me help. So why is there an S? What's the S for? Who's drawing the S? Just so you know, now you know what it's like for me when I have to try to draw on people's PDF documents or write on the documents. It's a nightmare. I must look like I'm 3 years old, like with a crayon going, ugh. Okay, so it looks pretty good. Looks like we have several people, Chris, right there. Looks like we have several people who are labeling axes as horizontally T and vertically Y. And that's exactly correct. That's exactly what the slope field would look like in terms of its axes. Now the question is, what kind of differential equation do we have? Is it dependent, remember, this is number 5, is it dependent on the dependent variable or is it dependent on the independent variable? What determines the slope?
The dependent variable.
The dependent, which means no matter where you look vertically, you're going to have the same slope everywhere. No matter where you look vertically, you're going to have the same slope everywhere. So what you do for number 5 is take a look at the graph that I gave you. That it looks like a polynomial graph, right? And figure out where are the y values that have a zero slope, And on that graph, you can tell based on where it crosses the horizontal axis, because the horizontal axis on that graph is y. So figure out those y values, approximate them wherever they happen to be, and now on your slope field that you've begun to draw, identify those y values, and they're going to be vertical this time. Identify those y values and put a dot along the axis for where you think you expect to see zero slope. And try to put them along the y-axis, because remember, it's all determined by the y value, the y coordinate. So far, so good. Looks like we're producing some y-axes. Thank you for owning it, Chris. I appreciate that. So we still have some axes that don't have dots on them for their identified where you expect to see a zero slope. Still got one. I'm waiting. You could just copy off the other people at this point. Come on. Really? Did you like disappear or something? I worry that you might have disappeared. Yeah, I don't know what happened to this person here, the YFT person. Makes me wonder what's going on. That's right. Yes, very good. Good job, Steve. You did it correctly. Okay, just so that we're all clear, you're reading the graph, and I'm going to kind of draw this on the background here. You're reading the graph that is f of y versus y. And it looks something like this. Let me see if I can remember. I had it up on the other screen, if I can remind myself. Oh, go away. Oh, thanks. Go away. It looks something like this. And that means here, here, and here. Those are the three places that we expect there to be zero slope, because this vertical axis represents slope, the sign of the slope and the size of the slope. And so here, here, and here are the y values. So two of them are positive and one of them is negative. So two of them are positive and one of them is negative. Now here's the question. In between this y value and this y value, what kind of slope would we expect to see on the slope field? What kind of slopes would we expect to see in between these two equilibrium solutions? And of course, how do you know? That's the follow-up. Take a stab. Even if you're wrong, that's okay.
It would be negative because it's below the y-axis.
So in between here and here, we would expect to see downward pointing slopes because this chunk of the graph right here is negative. It's below the axis. How about above this point right here? Slopes up here. Anybody but Emma, because she did such a wonderful job with that. What kind of
It would be
slopes would
positive
we? Because
it's above the y-axis.
yeah, all this chunk of the graph through here is above the axis. And how about in between this one and this one?
Also positive.
Also positive.
It's above.
And how about below this one?
Negative.
Negative. So we expect to see a slope field for number 5 that would have positive slopes above here, negative slopes in between those two, positive slopes between these two, and negative slopes down here. Can you visualize what that would look like for a slope field? And remember, everywhere else, all these at these points, they're all going to have zero slopes. So they're going to be horizontal lines all the way across at each one of those. Make sense? Yes. Yes. Thumbs up. Okay. When you guys were in like elementary school, did you play heads down, thumbs up? You did. They still play it. Oh, that's so good. I was like the champion of heads down, thumbs up. I was so good at it. That was amazing.
We called it heads up, 7 up or something like
It's
that.
up 7 up. Oh yeah, I was so good at it. I don't want to brag or anything, but I was the champion of the first grade. That's pretty good at that. And eraser tag. That was the other one that I was really good at. Did you guys have eraser tag? Of course you didn't, because they didn't have chalkboards when you were in elementary school, did they? Did they? Did they? Really? Matt, you had chalkboards? Damn. Where'd you go to school? Addison? Good God. Just kidding. Making fun of the Addison people out there. No, in the old days, they used to have those big chalkboard erasers that, like this big. And you had to, I think I've got one. Oh, I've got something that looks like a chalkboard eraser. And you had to put it on your head. And you had to balance it on your head. And you had to do tag around the room while it was balanced on your head. And it couldn't fall off. If it fell off, you were out. And I was kind of good at that too. I mean, I don't want to brag. Okay, so I'm going to clear this whole thing. By the way, you have the ability, you yourself have the ability, if you wanted to save this screen, you're like, damn, that really made sense. I want to save this for later. One of the annotation options is to click save. And by the way, you could do that anytime I'm sharing a screen. If you see something and you're like, damn, I want to save that, you can click save and it will save the screen with all the annotations on there, right? It's pretty handy. So I don't know if how many people knew about that already? Did you already know about that? Anybody? Sort of, kind of? It's pretty cool. It's pretty handy. The other nice thing is you can actually move the drawings. You can grab onto them and move them around. Unfortunately, one piece at a time, but still. So I'm going to go ahead and clear this drawing. I'll give you a second if you want to save it. Okay, so I'm going to save it, or I'm going to clear it. Boop, clear all drawings. And so my drawings still remain, because that's actually on a piece of paper underneath. So those two problems are the hardest problems in on that problem set. I really do believe that, because they require thinking about a graph that's on a set of axes like this that has well, I don't want to say nothing to do with. It doesn't look anything like the graph that you produce for the slope field. Number 5 especially. It does not look like the graph that's given, right? Turns out that the graph on number 4 kinda looks like the graph that you produce on the slope field. It's sort of polynomial-ish, but you don't get a polynomial slope field when you draw graphs like this. So here's the question. How can I, on Maple, produce a slope field for this? In other words, how can I come up with something to throw into Maple, some differential equation, dy dx, or dy dt, that is equivalent to whatever this curve is, this f of y? Can you come up with a polynomial that produces that shape? Dun, 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 dun. And just for giggles, how about I give them numbers? How about I call this -2, I call this 1, and I call that 2? Just for giggles. Those are the y values. I'll put numbers on them. Can you come up with a function of y that would produce that polynomial? Or something thereabouts.
About x plus 2 times x minus
Excuse me,
1.
what was the variable?
X? Oh, t plus 2. Right. Or is it y plus 2?
It's got to be a function of y.
Right.
So it would be quantity y
Plus 2.
plus 2 times
Y minus 1
times.
y minus 2.
And somewhere your pre-calc teacher is going, yes, finally they see the value in being able to create polynomials based on roots, right? Because if you know the roots of this function, you can create a graph that at least qualitatively looks like that. So guess what I can do in Maple? I can say dy dt equals this. And we can make a slope field. And it should look like this, where this is at y equals -2, this is at y equals 1, and that's y equals 2. So you do it. Make a slope field in Maple that's going to produce the slope field that we expect based on this polynomial. Do it. I'm going to stop sharing so that you can ponder that a bit.
How do I start a new worksheet in Maple when it's already open?
Up in the upper left, there should be just a tiny little document icon. You click on that and it opens up a new document. I think Control N also for new. I don't know. It's been a long time since I've
Yeah, that works.
rock and rolled. Okay, who's the first one to have it? It's Emma. Of course it is. Come on, Emma. Bring it on home. Share it with us. Show us what you got.
Okay, so disclaimer, I
Oh,
was a
come
little bit of a
on.
I was a little bit
Come
of
on.
an overachiever, and this is what I did for the homework actually.
Nice.
I
That's
kind of didn't
beautiful.
understand it at first, and I used 3 instead of 2, so I can change it if you want me to, but
2 of them have to be positive and 1 of them has to be negative. That's all that really matters, right? It doesn't matter the exact values, just that 2 are positive y values and 1 is a negative y value. Nicely done.
Thank you.
And you gave them different colors as well. Disclaimer. There's no disclaimer.
I was just
It's a
just
proclaim.
forewarning. I really was an overachiever here.
No, but the thing is, that's not overachieving. That's how you could produce this slope field, right? That's the way to produce it. Otherwise, you can't tell Maple, I need a slope field that has like equilibriums here, here, and here. Maple's going to go, give me a differential equation or else you don't get a slope field, right? So if you want to make a slope field in Maple, you can either hand draw it, snooze, or you can get Maple to draw it. But in order to do that, you have to have an equation, right? So nice work.
Thank you.
So
I'm
here's,
going to stop sharing.
yeah,
now?
go ahead. Okay. So I'm going to give you guys a test, and you, with your group, with your team, or not with your team, just by yourself for right now, see if you can figure out a way to produce a slope field that does this. Okay, you ready for this? You ready for this? You ready for this? Okay. Okay, I'm going to share my screen so you can see this. And I want to make sure everybody's clear on what I'm showing you. So what I want you to do is I want you to make me a slope field for dy dt equals f of t, as shown in this graph right here. Now notice, I didn't give you any numbers, so you're going to have to make some up, but they have to make sense for that particular graph. And by the way, that's f of t on the vertical, not f of y. Very tricky. How are we feeling about this one? Think you might have it? Silence. Yes. Okay. I want you to go to your breakout rooms and I want you to talk with each other about it and see if you can come to a consensus answer in your groups. Now that doesn't mean that you're going to sit there and one person's going to say, here's the answer, and everybody's going to go, okay. I want you to talk about it first before you share screens. Got it? Got it? Okay, go. I suppose I should probably pause rather than have you watch me just kind of chin stroke.